Good evening, ladies and gentlemen. How are we all tonight? Good. Well, welcome to this first edition of the 07 lecture series. Glad y'all could make it tonight. It was January 2004. Twin Rovers had successfully landed on opposite sides of Mars and were about to begin an ambitious 90-day surface exploration campaign. Well, 3 years later, Opportunity celebrated its 3-year anniversary just last night. With each rover only slightly hobbled by age, the campaign continues. Yeah, absolutely. Well, tonight's speaker is a planetary geophysicist who has been working at JPL since 1977. He earned a BS in physics and a PhD in geophysics at USC with a 2-year detour through Penn State. He was a global participating scientist on the altimeter instruments on Mars Observer and its successor, the Mars Global Surveyor, which produced amazingly detailed topographic maps of Mars. He was also on the Magellan Radar Science team, led the seismometer instrument team on the Netlander mission to Mars, and is a member of the acoustic sounder instrument team on the European Space Agency's Rosetta Comet mission. He has been working for the past 15 years to send seismometers to Mars and has a proposal under active consideration by NASA for just such a mission. Currently, he is project scientist for the Mars exploration rovers. His research interests are in the broad history of Mars and geophysical investigations of the interiors of the terrestrial planets using mathematical analysis backed by geological information and gravity, magnetic, topographic, and seismic measurements. Ladies and gentlemen, please join me in welcoming tonight's speaker, Dr. Bruce Banerdt.
Well, good evening, everybody. The title of my talk tonight's 2000 Sunsets, and I got to tell you, I'm only going to show you 2 sunsets. The talk was just getting a little bit too long with all of them. So, the reason why I call it 2000 Sunsets is obviously we've had over 2,000 sols or Martian days for each of the rovers. Actually, it's 2,158, but who's counting? And the sunset is actually a very important event every day for the rovers. So sunset means sun goes down, the temperature goes down, and it's the big temperature swings that are what will probably eventually kill these rovers, either the intense cold of the night or just the expansion and contraction when they get hot or relatively warm and then very cold. And so this is something that we expected to be very hard on the rovers, and one of the reasons why we only expected these things to last or designed them to last for 90 days. They've gone much more than 90 days, and we're really pleased about that. And I'm going to tell you about the last 3 years. As Mark just says, we just celebrated our 3-year birthday yesterday. We had 2 cakes, one for each rover, up in the Mars project area. And actually, one of the nice things about this mission, you have lots of parties, lots of celebrations, because you have Earth anniversaries, you have Mars anniversaries, you have 1,000 Sol anniversaries, so we're just partying all the time up there. Okay, so let's go on. Okay, so here's the same picture without the words, and I don't know if we can bring the lights down a little bit. There's something unusual about this sunset. I mean, the sun is over here, kind of on the right side of the picture. It's actually below the horizon. But if you think about a sunset on Earth, there's something a little bit weird here. I mean, on Earth, you have a blue sky, and the sunset is kind of orange and pink. And here on Mars, we actually have a pink sky, and the sunset's blue. And this is actually the correct colors, and it's because on Earth, the scattering happens from very, very tiny droplets of water in the atmosphere that are about the same wavelength as blue light. On Mars, the scatterers are dust. The atmosphere is extremely dry, and so we have a lot of dust in the atmosphere. The dust are larger particles, and so it scatters the red light, so you have an inversion in the sunset. And that tells us something, if you think about it, tells us something about Mars itself. And it tells us that Mars is very, very dry. Okay, so I'm going to go through a little bit of background on the Mars rovers and then try to at least touch on some of the science that we've done in the last 3 years. I've only got 3 hours to work, an hour to go here, so I'm going to have to leave some of it out. But again, they were originally designed for 90 days, 90 sols. So a sol is a Mars day, which is about 35 minutes longer than an Earth day. Currently, we're at 1068 sols on Opportunity and 1088 on Spirit, 1068 on Opportunity, and we've gone almost 10 kilometers and almost 7 kilometers for each of these rovers. And originally they were designed to go maybe a kilometer. That was our hope. Again, the temperature ranges from just above freezing to way, way, way below freezing. And it can vary as much as 80 degrees every single day. So this is what I was talking about before. We've had some hardware failures. We've had 2.5 motors fail. Okay, we have 2 motors which aren't working at all, and one which is sort of one of the redundant halves has failed on it, but it's still working. They were tested for 10 million revolutions, and we're currently at about 15 to 20 million revolutions for the drive motors, and way up around 50 million for the camera pointing motors. But of the 18 or 19 motors, we still have most of them working just fine. We've had some other minor failures, but the rovers are actually working really well after 3 years. And the science data return, we've gotten almost 170,000 images, and our mission success criterion, what we sort of signed up to do for NASA, was 2,500, so we're well in excess of that. And we said we would do, we hope to do 12 rock analyses, and we're up, actually about 120 now. When I made this slide, it was down 114. So this is a wildly successful mission by just about any standard. Okay, so why did we send these rovers to Mars? Well, we know that the Earth is a very wet place. You can look at the picture. It's blue. We've got nice white clouds, water clouds. So we can see from space that Earth is very wet. Mars, not so much. Mars is, you can see that it's red. That's not a watercolor. And all those white clouds that you see are actually carbon dioxide clouds. So there's very, very little water in Mars's atmosphere. But we're curious about what the role was of water in the past. We've got lots of evidence that there's water in the past. We've got canyons. We've got some rocks which from orbit show spectral indications of water. And so we wanted to go to Mars to find out more about what the role of water was in the past. So the mantra of the Mars program is follow the water, because water is an extremely important player in planetary geology, planetary history. In terms of the chemical, thermal evolution of the planet, it's obviously the weather and the geologic activity, and most importantly, in terms of its role in biotic and the prebiotic processes, the ones that can lead to life. So the MER, Mars Exploration Rover Science Objective, was stated in these terms. It was to determine the water, climate, and geologic history of 2 sites on Mars where evidence may have been preserved for past and persistent liquid activity that may have supported biotic or prebiotic processes. That was the charge that we got from NASA. Now the key to the history of water on Mars is contained in the rocks, because all this water activity must have happened very long ago. There's no water around now that we can find, or very little. There's a little bit in the polar caps, a tiny bit in the atmosphere, but not enough to really sneeze at. So this happened billions of years ago, and so we have to go to the rocks to find the evidence of what went on Mars. And to get the information out of the rocks, we need a geologist. So this is what a real geologist looks like. And so we went to the engineers and said, we need a geologist on Mars, okay? And a geologist has a pair of eyes. They can stand up, they can look around, see the scene. They can get down close to the ground. They can look at the rocks close up. They take a hammer along with them to break the rocks open, and they can have a backpack with some instruments in it to tell some things about the rocks. So the engineers went away, and this is what they came up with. So it wasn't exactly what we had in mind, but they said, no, this is exactly the same as a geologist, okay? And actually it is pretty close to a geologist. I mean, it stands about 5.5 feet tall, has a pair of eyes up here. It can see in stereo, so it can tell the distances of things. It can tell the shapes of things. It can look all the way around, can look up and down, and so it has a vision system which is very similar to that of a person. It also has down here an arm, and it's about the same size and the same capability as a human arm. It's got an elbow, a shoulder, and it's got a wrist, so it can get down and look at the rocks really close up. And inside that, at the end of that arm, it has several instruments, and up in the mast as well. Okay, first of all, we have the camera, which I also talked about. It has a mid-infrared point spectrometer, something that can actually look at rocks far away, and from the infrared spectrum, the signature of the different wavelengths of light off beyond the red end, it can tell something about what those rocks are far away, so it can see something that looks interesting, go up and look at it much closer. Okay, now at the end of that arm, it has a bunch of instruments as well. It, first of all, has this rock abrasion tool, which is the equivalent of the geologist's rock hammer. It's something that can actually grind down into the rock, get underneath the surface, because surfaces of rocks, when they've been exposed, especially for a long time, they can chemically alter. Even if there's just a little bit of water around or wind, it can change the composition of the outside of the rocks and get covered with dust. And so we want to be able to get down inside the rocks to find out what was going on inside those rocks when they formed. So that can remove the outer surface of the rocks, and it can actually has a brush that can just brush the dust off. And once it does that, it can look at the rocks with these two instruments here, a Mossbauer spectrometer, which looks at the iron minerals in the rocks, and the alpha particle X-ray spectrometer that can look at the elements. It actually tells, how much sodium, how much iron, how much oxygen are in the rocks. And with these two devices, we can tell what these rocks are made out of and compare them with rocks on the Earth. And when we know what rocks they are, we can tell something about how they formed and the conditions that were extant when those rocks formed. And we have a bunch of other cameras that help us to move around. We have some cameras down in front, which we call hazard cameras. They look right in front of the wheels, so if we're going to, roll off a cliff, they can warn us. We have a navigation camera, which is up in the mast, and it actually looks out very wide and can see a wide view. And the pan cam is our science camera, which has a very narrow view, but sees in very high resolution. So this is what they looked like before they left Earth. This is Spirit and Opportunity, and down here, this is the engineering model of the Sojourner rover that went on Pathfinder. So this is sort of the big sister of these two rovers. And we did some testing in the laboratory. I always thought this is a good test in case it runs into a sidewalk where the roots have kind of buckled it up a little bit. We haven't run into that problem, but we're ready for it. And we had to fold these things up inside this little tiny tetrahedron, and that was actually kind of an amazing process because these are pretty big robots. They're about the size of an office desk when they're unfolded, and we had to fold it up in something that's not much bigger than a little table. And once you fold it up inside this guy here, you encapsulate it in heat protection in order to get down through the atmosphere. You attach this guy so that it can actually go between Earth and Mars. It can communicate, can keep its systems warm, things like that. And you end up with something like this. So we have, this is what we call the interplanetary cruise stage. It has all its own systems, except it doesn't have any brains. The brains are actually in the rover, has a cable that's connected to it, so the rover actually has to fly itself to Mars, land, and then rove around on the surface. So it's a pretty capable little machine. So we have a heat shield that brings it into the top of the atmosphere, a parachute that slows it down, and finally we have these airbags that bounced on the surface, and you're probably all familiar with this stuff. Now, this whole entry, descent, and landing system has to get from the top of the atmosphere, where it's traveling at 5 kilometers per second. That's pretty darn fast. And by the time it drops to the ground, it has to be going only 5 meters per second. So we go from 50 kilometers high to 50 meters, 5 kilometers per second to 5 meters per second, all in less than 6 minutes. And this is really an amazing landing system. So we launched the two rovers back in 2003. They had about a 6-month trajectory, about halfway around the sun. We start here, go around, and we intercepted Mars about here. This is actually a pretty fast trip as Mars trips go, about as fast as you can get there. And this is what it would have looked like if we'd been able to sit on Mars and watch it come down. This is right before it lets go of the rovers down here and starts bouncing. Okay, so we landed at 2 places on Mars, almost halfway around the planet from each other. We landed in Meridiani Planum, which is a very flat area, and Gusev Crater, which is not so flat, but flat enough to be safe enough to land. So what I'm going to tell you about now is I'm going to go through each rover sort of individually, because these are really 2 separate missions. They land on different parts of the planet. You'll see they encountered very different conditions on the planet. So Opportunity, it's about 12 minutes after right now, 9:12 Pacific time, which means it's Sol 1069 and about 3:20 in the morning at the landing site B. And this is how far we've gone. We've gone, as of this morning, 9,978.98 meters. Okay, so Meridiani Planum. The reason we went here is because from orbit we have some spectrometers that were orbiting Mars on the Mars Global Surveyor, and it saw evidence for a mineral called hematite, gray crystalline hematite. Hematite on Earth almost always forms in the presence of water, and there were only a few spots on Mars which had this mineral. And so we thought that if we landed here, there almost certainly was water involved in the formation of these rocks, and we hope to find evidence of water on the surface. So we landed on Mars. This is a computer simulation based on the telemetry. It came down, bounced several times, and popped right into this hole. Now you can see there's not a lot of holes around here, so this is one of the most astounding golf shots of all time. So, and this is what we saw when we got down and we looked at that and says and this was named the Great Wall because we saw this huge wall, just covering the whole horizon. Of course, we found out later that this Great Wall, this is about 15 inches high. So there was a little bit of a perspective problem we had to get used to. But this was just a scientific bonanza because what we have here is bedrock. Okay, we've landed on Mars 3 times before. And we've never found a rock that didn't come from somewhere else. If you look at the Pathfinder site, you look at the Viking sites, lots and lots of rocks laying around, but none of them are actually attached to the ground. They've all been blown there, they've all been washed there, they've all been thrown there. They all come from someplace else, and a rock is an interesting thing, but it's especially interesting if it's in place, because that tells you what happened at that place at the time that rock was formed. And so it's not only the composition and the texture of the rock, but also its position with respect to the other rocks. It tells us about what happened here. So this was just scientifically, it was an amazingly lucky shot. So the first thing we did is we pulled in our airbags, and you can see the marks it made in the dirt, and we took some analysis with our mini test, our spectrometer, and what we could see here, we could compare the spectrum that we saw here in the yellow with laboratory hematite, and it has these 2 bands right here, which says, okay, we're looking at the dark unit, not those white rocks we saw, but sort of the reddish stuff all around, and we can see hematite. So that's the stuff that we came after. So we have to figure out where that is, and then find out what it looks like, and figure out where it came from. So this is now, instead of just looking at a single spectrum, we're looking at the whole picture, and in this picture, blue spots are spots that are low in hematite, and red spots are spots that are high in hematite. So we're looking here, and there's these places where the hematite was missing, okay? And they happen to be, you can see these patterns here, those are where the airbags bounce. So every place we bounced, the hematite disappeared, which seemed like kind of a weird thing. So we looked at it close up, and you can see the smooth places where the airbags made their impression, and you can see it's all kind of pebbly around here. So this gives us a clue. Well, maybe these pebbles are the hematite, but where did they go when the airbags hit them? Okay, so we looked at it close up. They're very round, which is kind of strange. And we look at it even closer up with our microscopic imager. I don't know if I mentioned this before, but at the end of the arm, we've got a microscopic imager, which is not really a microscope. It's actually more like a magnifying glass. So this whole picture is about 1.5 inches across. So you can get the idea of the size of these things. They're maybe 1/8 of an inch in diameter. So they're very spherical particles. These are what we nickname blueberries. They're not really blue, but they look like they're blueberries stuck in a muffin when you get to the rock. Okay, so this is an experiment we did where we actually pushed the arm down into the soil, and when you pushed it down, all those little pebbles disappeared, and that sort of was the thing that solved the mystery of the missing blueberries. Okay, so whenever the airbags hit, they just pushed the stuff down into the ground, and it got covered up with the dirt. So this is telling us that the blueberries, these little pebbles here, are probably the source of the hematite that we can see with our spectrometers on the ground and that we're seeing from space. Okay, so we moved off the lander and moved over to those rocks and looked at the rocks, and these are much different than any rocks we've seen on Mars before. Most of the rocks we've seen on Mars are what we call massive basalts. They're things that look the same. They don't have lots of little grains in them. They don't have layers in them. We've never seen layers on Mars before. These have these really fine platy layers, which is almost always evidence for sedimentary processes. And sedimentary processes is where the rock's been ground up, carried by wind or water, and then deposited somewhere and then re-cemented. This usually has something to do with water. And again, this is indirect evidence that water is going on here. Water is what we're after, and so we wanted to look at these rocks more closely. Okay, so this is a picture of rock. This is a pan-cam picture, and what we've done is we've stretched the colors way out. Okay, and when you stretch the colors, see everything here is kind of different shades of kind of orange and brown. If you stretch the colors out, you see that these little berries pop out as red, and everything else is blue. So they're not the same material as the rock. The little tiny spheres are something different than the rock that they're sitting on. And when we looked at it very closely, we found that they actually were in the rock. Here you can see one that's just poking out here. This is one that actually has broken in half. It's still stuck in the rock. So this rock here is made out of something. These are made out of hematite. And so we know that the hematite now, or we suspected extremely strongly that the hematite was in these berries. We have now a theory as to how these things work. They appear to be what we call concretions. When water moves through rocks on the earth, it dissolves some of the iron in the rocks, and when it gets to a situation where the pH, the acidity, has dropped, it actually starts to form these things actually inside the rock itself, and then it's exposed as the rock is eroded away. So these things on the earth form only in the presence of lots of water. The insides of the rocks are soaking with water when this happens. Okay, but we still don't know absolutely for sure that these berries are actually the hematite. So we figured out one more experiment we could do. We went to something called the berry bowl. We found a whole bunch of berries that were just kind of sitting on top of a rock like this, and there was a nice bare spot next to it. So we put our Mossbauer spectrometer down on top of the berries, and we put it down right next to it and looked at the spectra of these two measurements. And when we did that, okay, these blue peaks here, this is very indicative of hematite. Hematite's the only mineral that makes this particular signature. Okay, so we put it on the berry bucket. We got these big things here. The yellow spectrum is when we put it right next to it. So this was finally proof positive that the berries were the source of the hematite. And since we had now an analog on the earth for how those things formed, we now were very confident that we could say that these rocks, when they formed, were formed in the presence of water, and lots of water, over a fairly extended period of time. And this is something that we didn't know before. We couldn't tell that from orbit. We knew that there was water for short periods of time, at least on Mars, but this was our first proof that water actually was present, at least in the subsurface, for long periods of time, billions of years ago. Okay, so the next thing we'd like to know is what the rest of this rock is made out of. Okay, we know the little berries are made out of hematite, and we know the rest of the rock is something else. So we took the rock and we ground down into it, and we looked at the composition. Okay, now this is a little bit hard to see, but you can see here you have this red stuff here. The red stuff is just the composition of the soil, just the dust, and the dust is the same just about anywhere you go on Mars. The blue peaks here are the composition of that rock that we just looked at once you've taken the soil off the top and once you've ground down into the interior of it. And you can see that you have a big peak here, which is sulfur. You have another peak over here, nickel. You have a peak at bromine, and you have a little bit of extra chlorine here. Now, these are all things that are mobilized by water. And again, this rock is something that's been affected by water. That's had these elements dissolved from someplace else and concentrated in these rocks. And we look at with our other instrument, the Mossbauer spectrometer, and we're able to identify this particular set of peaks, again with a mineral called jarosite. Now, see this little OH here? Okay, that's basically pieces of water. This rock has to form in the presence of water and in the presence of lots of water. So not only did those berries form with water, the rock itself formed with water. This is a sandstone that has seen lots of water running through it. It's changed the chemistry of it, and in fact, we know something about the conditions under which this formed. It couldn't have been too hot, and we know that it had to be extremely acidic. Okay, it'd be more acidic than some of the acid runoff that we get from mines even, because that's the only place on Earth that you get this jarosite forming. So this told us that when these rocks formed, it was wet, it was warm, and it was very acidic. And this actually solved a problem that we've had for a long time on Mars, And that is that if there was water on Mars, we expected to see a lot of rocks called carbonates. We have lots of carbonates on Earth. If you have water and you have carbon dioxide in the atmosphere, you get carbonate rock formed in the water. But it turns out that if you have very acidic water, carbonates can't form. We've never been able to find any carbonates on Mars, and there was lots of theories about how it got covered up or it got taken away, this, that, and the other thing. But this now gives a plausible reason why we never found carbonates on Mars, which is something we've been looking for 10 or 15 years. Okay, more evidence. We always like lots and lots of evidence because you're never absolutely sure. This is a rock called El Capitan, and if you look at it closely, you can see a lot of little kind of, looks like little cracks in this rock. But you look at it close up, and you can see some of these star-shaped things. These are actually little voids in the rock, and they're kind of lens-shaped. When we see this on Earth, they're usually caused by crystals, which were formed in the rock and then have later evaporated, dissolved away, and again left these cavities. And so this is yet one more piece of evidence for lots and lots of water in the rocks. Okay, so everything we've seen so far has to do with groundwater, water underneath the ground in the rocks, just seeping through the pores in the rocks. Okay, but when we saw this particular set of layers here, this is telling us another story. You can see that these rocks are stratified, okay? You have this lower unit, you can see that the layers are very ripply. In this unit, they're very flat, and then they're rippled again in this unit. Well, that tells us something about how these rocks were deposited at the surface of the planet, okay? Rippled rocks generally are formed under aqueous conditions, conditions where there's water, and it's not just water sitting there, it's actually water flowing along. That's, you get ripples in the bottom of the streams, and given the gravity of Mars, the dimensions of these ripples are the dimensions that you expect for flowing water. Not flowing very fast, but flowing on the surface. So these rocks almost certainly were deposited in water at the surface of the planet. These are planar, okay, they're very flat. That typically happens either in a lake bottom where there's not much going on, or is deposited by just dust falling out of the atmosphere. Not much action going on, not much lateral velocity. And then again, we have the ripple layers up here. So this is telling us a story about what went on here. You had a material that was deposited in flowing water, it dried up, you have things deposited on top, then you have flowing water again. So we're starting to see a history here of what went on. This is a close-up, and we can see this in a little bit more detail. I don't know how to draw these lines, but geologists can draw these lines really well. And what we see here are lines that intersect, okay? Instead of having, this is in the rippled layer, this is what we call cross-bedding. And cross-bedding is something, again, which happens when you have ripples moving across a plane. This is an example from the Earth. This is from Zion National Park in the sandstone. And you can see where these things come in and they meet at angles. And here you have the planar layers. Here you have the ripple crossbed layers and the planar layers. And so by looking at similar rocks on the Earth, we can then extrapolate to Mars, and we think that we have some idea of how these things formed on Mars. So basically at this point, we've satisfied all of our requirements. We spent almost 60 or 70 sols in this little crater, and at that point we could rest on our laurels, but we've got a nice healthy machine here, so we decided to leave this little crater. This crater is only about 5 meters across, about 15 feet. And we're going to head for Endurance Crater. Okay, you can see this is a little less than a kilometer away, but quite a bit bigger than the little crater we started off with here. This is about 150 meters across, about 1.5 football fields. And the thing about a big crater is it's a big hole in the ground. And when you have a big hole in the ground, that means that you can get down. Okay, now instead of taking a drill along, which would have been a pretty difficult thing to do, but instead we went looking for a crater that dug the hole for us. So when we got to Endurance Crater, it was everything we'd hoped for. You can see these cliffs on the side of the crater, and look at this layering here. Okay, whereas before we were looking at something, maybe the thickness of this dark line here in Eagle Crater. Now we've got this big thickness here, and just for scale, that's about the size of the rover. So you can see the rover's about 5 feet tall, so we've got about 10 feet of layering here to look at. And for geologists, thickness is equal to time, and so we're looking farther and farther back in time as you go down through these layers. Okay, and we had this tantalizing information from the PanCam that showed that when you stretch these colors, you can see that the rocks at the very top are much different than these rocks in the middle, which are again much different than the soil that's overlying these things. So we knew that there was some kind of story here to be told. So we decided to go down into the crater. We did some tests up in the Mars yard here at JPL and determined that even though we hadn't tested the rovers originally to go down into slopes this steep, that they were perfectly capable of doing it as long as we stayed on top of rocks and didn't get into loose sand. And so we went down the crater, and as we went down, we did analyses. Okay, so if you look real closely in the middle of each of these circles, you can see a little bit of a hole in each one of these. We made a real mess going down in here. National Parks would have never let us get away with this. So we went down. All those holes were in this little area here. We did more and more all the way down into this crater, and this is going to give us a stratigraphic section through the rocks over about 10 meters of vertical distance. And we found some substantial changes from the top to the bottom. Okay, this is what the rock looked like when we ground it off near the top. You can see that it's a kind of a soft rock, but it's fairly competent. It's got these layers in it. By the time we got to the bottom, it was much more crumbly. It just kind of fell apart. There's no layers left in it. This is a much older rock, likely much older rock than this one. And we know that geologically speaking, rocks always get older as you go down. But in this case, we have some substantial evidence that it's much, much older. And we can see trends in the chemistry as well. Okay, now we have sulfur and magnesium. Okay, these rocks that we're looking at, the jarosites, those are sulfate rocks, which mean that they have a lot of sulfur in them. And the sulfur and magnesium are there in about the same proportion. So since the sulfur and magnesium go pretty much together, we see that this is about the same kind of rock as we're going down. But look at what happens to chlorine. Chlorine increases substantially from up here. It's fairly low, and it gets much, much larger up here. In fact, we've got a little break here. It's just to keep it on the same scale. So chlorine increases as you go down, and it turns out we have similar trends with some of the other trace elements. Bromine actually decreases as you go down. So this tells us that all these rocks weren't deposited under the same conditions. What's happening is that chlorine is a component of salts, which are soluble in water. So this indicates that perhaps you had a change in the amount of chlorine that was available, the amount of salt that was available in these waters. So not only are we getting differences in the acidity of the water, we're getting differences in the saltiness of the water. And these are all chemical clues as to the environment. Okay, so then we went up to this cliff that you could see from the images before, and you can see lots of layering here. We spent a long time looking at this cliff in a lot of detail. We didn't just look at this one section. We went all the way along it, as far up and down as we could get with our imaging systems, and we're able to put together a story. Okay, and this was the conclusions of the team, that we have this stratigraphic column. And just to make a long story short, we had the same kind of conditions sort of spread out as we found in Eagle Crater. We have these layers at the very bottom, which are cross-stratified, but they're cross-stratified in a very coarse way, which is what we see in sand dunes on the Earth. We have a planar layered unit in the middle, which is something we expect from a sand sheet, something which is not mobile, just a bunch of sand that's been deposited there. And then we get up to the top and we get this ripply stuff, which was probably deposited underwater. All these rocks are approximately the same thing. They're all this kind of dirty evaporite sand. Evaporite is what you get when you take a lake, you evaporate all the water, and you're left with these salts. You see the salt flats out in the desert. Those are evaporites, and we have that mixed in with this sand. So even though these things are all roughly the same kind of material, they were deposited under very different conditions. And the conditions in particular were very oxidizing, very acidic, and very saline, high in salt. So only in a few places along here do we have evidence for water that's persistent. And so although the conditions when these things were deposited were probably habitable, they would pose real challenges for origin of life. It's really hard for life to start in acidic saline solutions. So this is something that's a challenge that the astrobiologists are looking at. So we finished up at the crater, and we went a little ways longer. We checked out our back shell and our heat shield, and we found this strange rock. When we looked at it, the spectrum looked like the sky, and we found out it was just reflecting because this is an iron meteorite, which no one expected until they thought about it and said, oh yeah, meteorite's been hitting Mars for 3 billion years, so why not? So after about a year and a little bit, we'd finished up everything that was high priority science at Endurance Crater, and we still had a rover that was nice and healthy, so we thought, well, what should we do next? The thing about Meridiani Plains is it's very, very featureless. But there's this other crater down here, Victoria Crater, and you can see that this is much, much larger, again, than Endurance Crater. So if this got us, farther down into the deep layers of the planet than Eagle, just think what Victoria might do. Although 5.5 kilometers, we'd only gone about 1.5 kilometers at that point. That seemed like a pipe dream, but we thought, well, what the heck? We'll just put the pedal to the metal and see what happens. And this is what it looks like. This is looking back at our path. You can see here's the tracks just going off in the distance. It gives you, again, some idea of how flat and featureless these plains are. All we have are these sand ripples as far as the eye can see. And some of those ripples are deeper than others. This is where we got stuck. We were just driving along, and the rover drivers were planning longer and longer drives every day. Everything looked fine, and then one day we had about 50 meters of odometry on the wheels, but it only moved about 6 inches in all that time. And so we looked at it, and you can see here where the wheels are dug in about 3/4 of the way into the sand. This is actually a self-portrait where we had the cameras actually looking down, moving all the way around, and so you can see most of the rover itself, and you see these dunes here, the tracks coming up, and then we're just stuck in this big ripple coming along here. So we did a lot of work in the sandbox over here at JPL. We spent almost 100 days there trying to figure out what to do, and in the end, the conclusion was put it in reverse and back out. And that's what we did. And after about 2 weeks of backing up and only moving, a couple of inches a day, we finally got out of the sand dune. But that's what happens when you have a whole committee of people and managers deciding how to get out of unstuck from the sand. Okay, so as we're going south, we passed some very degraded craters. This was Erebus Crater, and Erebus had this one outcrop which had the most, the strongest evidence yet. I mean, these are really clearly water lane. No one can figure out how you can put down ripples like this without water. So this is sort of our type example now of water lane sediments on Mars. And so as we got closer to Victoria, we found, instead of just the sand dunes, we found some of these areas with rocks. These are just pebbles, but you can see these are very dark colored pebbles. That was telling us there's a contrast between the surface rocks and these rocks. Maybe these were something that was thrown out by Victoria. Maybe we really are seeing below this layer of rock that we've been looking at so far. And finally, after almost 1,000 sols, we reached Victoria Crater, and this was our first view across the crater. This is about 2/3 of a mile away here, about half a mile away, and you can see these cliffs here. The depth of this crater is about 50 meters, I think. So this is, again, about a factor of 4 or 5 deeper than we saw in Victoria. It has these great cliffs looking out across. This is a picture of Opportunity sitting on one of these points. This is a fake picture. That's not the real Opportunity. But it turns out that since it took us so long to get there, NASA's put some other things up in orbit. This is a picture from the Mars Reconnaissance Orbiter, taking a picture of Victoria Crater, which we're actually using for playing some of our drives. And if you blow up this thing right here, there's our rover right there. So this is not a fake picture. This is the actual thing. And in fact, here it is. Here. You can even see the shadow here of the camera mast. The camera on MRO is that good. And it really does move. we were pretty confident of that, but the fake moon landing people, really weren't going to believe us until we could show them pictures. So. Okay, and we've been moving, working our way around Victoria. Our plan is to go out onto these little points. Whenever we get to one of these points, we take pictures across this way, we take pictures in the other direction, and so we're mapping out the layers in each of these points as we go along and trying to correlate the layers as we move around the crater. And this will give us our first chance at looking at the layering below the surface in 3 dimensions. We're trying to go maybe a third, halfway around the crater, and as we're doing that, since we're going back, we're shooting our photos back and forth. We're building up a stereo image of the crater, which will give us slopes, and we hope sometime in the next year or so to find one of these ramps which is shallow enough slope to actually go down into the crater and do the same sort of thing we did in Endurance Crater and look at some of these layers in the sides. Just to give you an example of some of the things we're doing so far, this is one of the points. I'm going to blow up this section here. This is an example of some of the geologic analysis that's been going on. You can look at this cliff face, and you can see a break here between this layer, another layer here and here. This is just all jumbled up rocks. You can see some layers sticking up here. You can see other layers that are sideways. These are all rocks that were thrown up by the impact and fell back down again. If you look at these rocks here, they're all about the same direction, if you can see the layering in them, but it's all cracked and fractured, so they're pretty close to where they started out with, but they're very heavily fractured. And then you have this layer down here, which we term bedrock. This is stuff you can actually trace these little lines for long distances in here. And we've seen this kind of a stack in each one of these points as we went along. And this is especially what we're interested in here. This is the stuff that's in place, and we can tell something from this layering. Again, we're seeing evidence for cross-bedding. We're seeing evidence for sedimentary processes in here. Okay, so let's move to Spirit now. Okay, if I'm on schedule, and I'm a little bit behind schedule, not so far. Spirit is almost 1,090 days on the planet, and it's about 3 o'clock in the afternoon, almost 4 o'clock at Spirit. You can see the other one was 3 o'clock in the morning. This is 3 o'clock in the afternoon. So when I say 2,000 sunsets, these rovers never see the same sunset, okay? They're always seeing the sunset on opposite sides of the planet. So it really is 2,000 distinct sunsets here. Okay, so Spirit we sent to a different kind of a landing spot. This is Gustav Crater. This is about 150 kilometers across, about 100 miles. And you can see this meandering channel here that looks like it's dumping into this crater. This was thought, just from orbital imaging, to be a lake, at some point in the distant past. This channel was almost certainly carved by water. You can even see a place here where it maybe spilled out again. So we figured if we went here, we would probably be able to see a really thick section of rocks and dirt that was deposited by water and be able to use those rocks to tell what the conditions were in that water. And when we landed there, it looks just like Pathfinder, it looks just like Viking. Just dirt and all these rocks. Again, all these rocks have come from somewhere else. Doesn't really look very sedimentary, but we're going to do some analysis. We found a big rock with a nice flat surface, and we ground into it. Looked at the composition, and it looked like an olivine basalt. And we know that most of the rocks on Mars are olivine basalts. This is a volcanic rock, and most of Mars's crust is made out of these volcanic rocks. And okay, so this is a volcanic rock. It's not a sedimentary rock. There's no layers in it. We looked at the texture of it. You can see all these little crystals. Again, this is olivine, and when you get down into it, it's even more olivine-like. So this is definitely an olivine. This is a demonstration of why it's important to get under the skin. Okay, each of these bars is the analysis for one of these elements. Okay, so we have silicon oxide, sulfur oxide, chlorine, potassium. The last 4 of these are different analyses of dirt. And then this first one is the surface of this rock just without doing anything to it. The second one is, this is the soil again. This one is the surface of the rock, which is very dirt-like because there's a lot of dirt on the surface. Here we just brush the dirt off the surface. This bar goes down a little bit, which means the sulfur's gone down a little bit. And this last bar is when we ground into it, the sulfur's gone down even more. So what this tells us is that the dirt at this site is high in sulfur, high in chlorine, high in potassium, because all these things go down as you brush the dirt off, and the surface has reacted with this stuff. So in order to get down underneath in order to get to the actual composition of the rock, you have to grind underneath the surface, and this was sort of a verification that it was a good idea to bring this rat along. When you get down to these levels, these again are basalt levels. This is typical of weathered rocks on the Earth. So what we're seeing is a weathering rind, the reaction of the skin of the rock with the atmosphere over time. Okay, so that wasn't very interesting. I mean, it was interesting, but it's not what we came after. We didn't come after volcanic rocks. So we thought, well, this works so well with Opportunity. Here's a big crater. This is about 200 meters across, even bigger than Endurance Crater. So we're going to head along here and check out this crater. Okay, and you can actually see the tracks. This is the Mars Observer camera image of the rover. You can just barely see the spot here. But when we got there, it was a big disappointment. All we found was a big bowl of dirt. Okay, this is an old crater. It's been filled in with sediments and things. There's no cliffs. There's no bedrock sticking out. It's a lovely old crater, but again, everything around here is basalt. And every time we saw a new rock here, a little bit lighter, a little bit darker, something that looked like maybe it had some bubbles in it, we'd rush over there and put our instruments on it, and every time it was just another basalt, exactly the same composition over and over and over again. So Spirit was looking pretty much like a bust at this point. You know, we could look at basalts, but we'd already looked at those with Pathfinder, and there was nothing there to indicate water. Here we are in this big lake, and there's nothing to indicate water. So again, we're looking over here on the horizon, and there's these hills over here. And these hills are several hundred meters high, and we thought, well, maybe there's something interesting over there because there's certainly nothing to do here. And again, it's a ways out there, so we headed for the hills. And this is about 3/4 of the way there, and you can see, you know, it's sort of like driving across the country. You know, you drive and drive and drive. They still look like it's forever out there. And you know, every once in a while you have to do something interesting just to keep from falling asleep. But we finally, after about 155 sols, we finally made it to the foot of these hills. Okay? And at that point, everything changed. Okay, the first thing we saw was this rock, which we nicknamed Pot of Gold. And look at the shadow of this rock. You got all these weird things sticking out here. This is clearly not your father's basalt. I mean, this is something completely different. And from then on, everything that we've looked at in these hills has been completely different than what we've seen in the plains. We took a path all the way up to the top of the hills, analyzing things as we went along. Oh, and this is another interesting thing. One of the reasons why we didn't expect to last very long was the temperature cycles that I talked about. The other thing was the fact that at night you need power in your batteries to stay warm. And in the wintertime you need a lot of power. And we knew that with these solar panels from Pathfinder that dust accumulates on the panels. And we calculated that after about 400 days on Mars at the very most, we wouldn't have enough power to operate anymore, and we would just be dead. Okay, so this is looking at a self-portrait again. You can see everything but the camera that's taking the picture, and you can see that the panels are very gray. We were pretty low on power. It happened to be in the middle of the summer, so it wasn't too bad, but we were looking at maybe another 4 or 5 months on Mars at the very most at that point. And here it is about 100 days later. Look how clean these panels are. This is just like it left the shop. What happened was we had a panel cleaning event, okay, and we don't know exactly what it was because we don't have the instruments on there to pay attention all the time, but almost certainly this was a dust devil that came across and just cleaned all the dust off the panels. And this happens every spring, it turns out. We've taken some movies. I didn't put anything in here about the atmosphere because I didn't have time, but we've taken movies. You can see dust devils moving across the plains, and we can see the tracks in orbit even from the dust devils where it cleans the dust off the rocks. So because we have these springtime dust devils, we've actually been able to stay on Mars for 3 years instead of only a year or so. And this has happened every spring, and springtime's coming up right now, and we're crossing our fingers and waiting for the dust devils to come and take care of us. So this is our path up Husband Hill. This is what we thought was the highest hill in the Columbia Hills. It turns out McCool's a couple meters higher. So we came up here, and at each of these points we made an analysis of a rock that looked a little bit different. Okay, and these are just the funny names that we gave to them. And another weird thing we found, when we were scuffing up the soil, we saw something white. We went back and looked at it. It's a place called Paso and it's quite different. You can see the white soil here. We put our instruments on here, and this is basically salty soil. This is some salts that were just below the surface. The only way we know that these salts could have been deposited there, you have seen them at the surface, they're just below the surface, was the way it's done on the Earth, which is moisture coming up from below the ground, gets up to the top, it evaporates away, and deposits the salt that came up with it. So somehow this salt's getting concentrated just below the surface, and that almost has to have something to do with water, probably water in the not too distant past, because the surface of Mars is being gardened by meteorite impacts. It's being blown around by the winds, and so this had to have happened not too long ago. And it's actually quite puzzling. We're not sure exactly how that can happen, but this is something that we've seen in a couple of places now. Okay, so this is just the spectrum that shows us that it's salt. So we found 5 new classes of rocks, none of which are the same old basalts. And this is just a composition diagram. We have different elements here, and if they were the same as the basalts in the plains, they would have all those points would have been right along here. And you can see they're going all over the place, okay? And especially elements like potassium, chromium, phosphorus popping up here. So these things are, again, things that are mobilized by water. So these rocks have been affected by water. They generally have an overall composition similar to basalt, but they've been metamorphosed by the presence of water. Okay, and we've got layers. Finally, we have layers. Geologists love layers, and geologists love these hills because there's lots of layers. Some of these rocks look similar to the basalts we saw below, but this particular rock has concentrations of trace elements that are completely inconsistent with a volcanic rock that hasn't been altered. Again, we have a rock which looks like a basalt in composition, but this is a sandstone like we saw for Opportunity. Another strange rock, lots of different kinds of rocks. Here we found a rock which has very, very low iron content. Almost everything on Mars is very high in iron. This one had very low iron content. This is a couple of our rock types mixed up together. And this was an outcrop which was a very unaltered basalt. And in fact, the thing about basalt is if you put water on it, it oxidizes. There are little crystals in it that just turn into dust, turn into rust. And we saw none of this in here. So however this rock formed, it must not have seen much water, which is completely opposite of what we're seeing everywhere else. And so we put together a story for the Columbia Hills. And first of all, it's clear that the geology of these hills is completely distinct from the plains below. They seem to have formed by an impact or by explosive volcanic deposition. The rocks that we see don't show any ripples. They show layering, and they have features in them that indicated that perhaps these occurred just by falling from the sky. And the way rocks get thrown up in the sky is by explosions, and the two ways that you get explosion is either by impacts or by explosive volcanism. Most of the rocks recorded a common presence of water during and closely subsequent to their deposition, but there's lots of evidence that they've been dry for most of the remaining time, and by extrapolation we can conclude that this area may be typical of the ancient Martian crust, something we didn't expect at all when we came. So when we got to the top of the hill, we've gotten all these rocks. We have lots of stuff to analyze, but again, we still have a healthy system. So we decided to go down the other side into an area called the Inner Basin, which is ringed on 3 sides by these hills. And in particular, there's this weird thing down here, which is called Home Plate. It's kind of pentagonal structure. And we can see this from orbit. And it's a very light feature. We thought this might be something interesting. And right here is Low Ridge, and that'll pop up again in a minute. Okay, on the way down, we saw the sand dunes, and the sand in these dunes was very spherical, which means it's well sorted. It's been moved around a lot by wind. It's almost pure basalt again, could not have been exposed to water at all. When we got to home plate, finally we found some layers that were in place. Most of the layered rocks we found on the hills were jumbled up. They weren't really bedrock in the normal sense. This is clearly a structure which is bedrock. And we found this funny thing here. This is a rock which apparently is coming down, and you can see that the layer that it's in has been bent down like this. On the Earth, that happens in a volcanic explosion where these layers have been put down by volcanic ash. It's kind of muddy, and later a rock comes down, goes plop into it, and actually pushes the layers down. So this is something that we think is evidence that this home plate was deposited by volcanic ash and by a volcanic explosive volcanism from an event that was not very far away. So home plate was the first clearly depositional feature we've seen with Spirit. But we didn't get to look at it very long because winter was coming on. We needed to get to a place where we could tilt our solar panels towards the north because we're in the southern winter. And because it gets so cold, because we're far enough south that the sun is sort of disappearing over the northern horizon a little bit, we needed to tip our solar panels in order to stay alive during the cold winter. And so we left home plate, and almost the first thing that happened was our right front wheel failed. Okay, and here you can see, here's a nice tread prints from one wheel, and here's a nice furrow that we're digging with the other wheel. And of course, this happened at exactly the wrong time. We had about 30 days before our power was going to get too low. Here's our power plot. This is the trend that we were on. This is where our wheel seized up. At about somewhere in here, you can't drive anymore, and somewhere down about here, your rover dies forever. So we only had about 30 or 40 days to figure out what to do. And so we tried to drive, we got stuck. We ended up turning around. Here's where we're coming from home plate. Our wheel seized up about here. Here we're digging up ground, trying to get to this hill here, and decided we couldn't do it. So we decided to back off to our sort of plan B position. Here you can see us dragging this wheel to this position here where we were able to tip our solar panels, get up on this low ridge, which was tipped north, and get a good power situation. And you can see here, this power coming up here is when we tilted about, tilted about, I think 7 or 10 degrees to the north, increased our power by this much, and so we went down along this trend instead of along that trend, and were able to survive the winter. So that lasted about 200 days. We just sat still for 200 days. This is another picture from high-rise on the Mars Reconnaissance Orbiter. Here's your home plate. We're parked about there. And if you look at it, again, here's our rover. You blow it up, and again, you can see the shadow of the PanCam mast. We're sitting on this ridge and tipped up towards the north. And now you can see here the details of this. And in fact, if you look at this in stereo, you can see this is something that's poking up. This is a big hole here. We've got lots of interesting geology to examine. But we had to figure out something to do with our time for these 200 days. So how Spirit spent his winter vacation is taking this picture right here. It took 6 months to put together this picture. This is a full resolution panorama over 360 degrees with all 13 filters. We have lots of different filters in this camera, which allow us to see not only the different colors, but see some of the infrared wavelengths as well, so we can do a little bit of spectroscopy with it. We not only had very little, well, because we had very little power, we could only wake up for about a half an hour every day, so we just took a little bit of this picture at a time. We had to do it at about the same time of day every day so that the shadows were right. So after about 6 months, we were able to put together this panorama, which is an amazing, amazing tool for looking at the geology of this area. What I'll do is I'll look at a couple of these things in more detail, just zoom in on this picture. And this first one over here is just a picture of home plate. This little streak here is home plate. That's Husband Hill. We started up at the top of that and we came back down here. And just to see how good the resolution is, we can zoom in again. Here you can actually see the layering in the side of home plate here. And this is quite a ways away, and you can see that was just a tiny little piece of that McMurdo panorama. We also found another new rock. Okay, this is called a vesicular basalt. You can see that this looks quite different. This is like our normal basalt, what we call a massive basalt. This is all full of bubbles. Okay, bubbles tell us that when this rock erupted, it had a lot of gas in it. Gas comes from volatiles. Volatiles means water. So again, this was part of a very wet eruption, probably an explosive eruption. We hadn't seen this anywhere on Mars before. Another thing we saw is another couple of meteorites. Here we found two meteorites sitting next to each other. No one can figure out how you get two meteorites sitting next to each other. That seems probabilistically impossible, but here it is. So they're working on trying to figure out why that is. And look at this thing. These thin platy layers. This is sticking out about 10 inches. You can see the shadow down here. This is a diving board. There's another one up here. We have no idea what this is. This is, again, some completely new rock. This is the meteorite that was in the other picture. Here's some pieces that have fallen off. We can't get to this stuff because it's too far up a slope right now. Because our wheel failed, we can only get up about 10 degree slopes. And this was about an 18 degree slope, so we'll never be able to figure out what this is. But we're trying to extrapolate that around here and get to the same material. We think perhaps this is the same material here. This is troll outcrop. This is where the rover is right now. We've been doing some analyses on this layer here. You can see that there's a difference here. There's this light layer here with some layering in it. Then we have this layer 2, which I'll show you in a second. These are the names that we give some of our analysis point. And then perhaps even a third layer up here. If you look at this middle layer, it's made up of a rock with all these little tiny spheres in them. And some of the geologists on the team think these are blueberries halfway around the planet. They're very tiny. This is only about 1.5 inches across this picture. But we think that perhaps this may have been formed by some of the same processes that formed the rocks way across the planet in Meridiani. And then we have this thing here, which is, you can see some of these layers that have been broken off, and we hope to get on top of this one as well to do some analysis. So what's next? Okay, we're sitting down here. This is where we've only gone about 5 meters from our winter vacation spot. We want to go back up here, check out some of that white material that we dug up when our wheel broke to see whether that's the same stuff we saw up on the top. Then we hope to go back up onto home plate and maybe use this on-ramp. We can't go up the slope, but it looks like we've got a ramp that can come up here, get back up on top of home plate, either go out into the middle and do a transect across here, looking at the different rocks across the radius of this deposit, or come around here and head out here. Again, we've got a rover. It's got 1 broken wheel, but we can move fine with 5. Everything else is healthy, so we're looking forward to a lot of good science. And here's your other sunset. This is a sunset across Gusev crater, and this is the morning star on Mars, which is Earth. Thanks. So I guess I have time for a couple of questions. Yeah.
Yes. Do we know what home plate actually is? Is it like sort of an uplift? It looks like a plateau of some sort, but what actually caused that to take place?
We don't know what home plate is, but we've got some interesting clues. We looked at the layers as we went around, and it turns out that we've gone about a third of the way around home plate, and everywhere we look, the layers dip in towards the center. Okay, so that tells us that this thing was deposited as a bowl shape. That can happen a couple of different ways, but based on the fact that we have evidence for some volcanic stuff, the fact that the rocks look like tough deposits on the Earth, which are volcanic ash, we think this is some kind of perhaps a volcanic vent that threw out some ash and then fell back in. There's some tough cones that have that kind of morphology. This is just speculation right now. That's one of the reasons why I want to go back and try to test some of those hypotheses. Yeah.
My dad said that that they're gonna that they might send another robot up there that's gonna sit down and it's not gonna move and it's gonna drill down to see if there's any water underground.
Well, there's another spacecraft they're going to launch next year called Phoenix, which is going almost up to the North Pole, and it doesn't have a drill, but it has a claw that is going to try to claw down and get into the ice. They think there's a lot of ice just below the surface. And then a couple of years later, there's another rover that's going to go, which I don't think it has a drill on it either, but it's going to be a bigger rover to look at the rocks in a lot more detail. We're thinking about drills, but drilling's a really hard thing to do on Mars because drills are complicated machines, and we haven't figured out quite how to do that and be sure that it works. Yeah.
What are you seeing in terms of the angles going down into the Victoria crater? You know, what angles are you seeing? What angle do you need to get in order to start to think about going down in?
Well, the preliminary analyses, we haven't finished the stereo bit, but the preliminary analyses it looks like there's a couple of places where the angles are down around 18 degrees or so. And we can go down pretty confidently at about 25 degrees. We can come out at about 20 degrees. And so, you know, it's right on the edge now, and that's if we have rock. You know, if it's just sand or dirt, you know, all bets are off because we just slide. So indications are there's a couple places that we're pretty confident we can go down. Not so sure yet that we can get back out again. Although there's a lot of sentiment on the team that you know, we've been going for 3 years. These things aren't going to last forever. The good stuff's probably down there. So even if we can't get out, it's probably worth, you know, going down there and taking that chance. But that's a discussion that we're going to have over the next couple of months.
What's the diameter of that abrasive device? And another question on the wheel, that's dysfunctional. How do you move along with that? Can you raise it up, or you just drag it along?
Well, the diameter of the wheel is about 4 centimeters, a little less than 2 inches, about like that. Yeah. As for the wheel, we can't. You know, the suspension on these rovers is completely passive. It's a really clever design that allows it to, you know, comply with the rocks, but it's all just gears, and so it's built to keep all 6 wheels on the ground all the time. Which, when you got the wheels all turning, that's a good thing. When you have one that's stuck, that's not a good thing. And this wheel's stuck; it can't turn. There's no way to disconnect it from the motor, and you got a gear train that just sticks. So we can't pick it up, we can't let it turn, we just have to drag it. Yeah.
Based on Burns Cliff and now on Victoria, do you have a best guess upper-lower limit on the water, the depth of the water, and the duration of the water? Can you put any kind of limits on them?
Not really. I mean, what we see in Victoria is we see evidence for cross-bedding in the lowest layers that we've been able to see, which is about 20 meters down. So this is a fairly thick unit. Now, you go to the Grand Canyon, you have a whole mile of this stuff sitting out there. So, you know, 20 meters isn't a lot. As for the time, it's anybody's guess. You know, this stuff, you know, sand dunes can move a lot of sand in there in a fairly short amount of time. On the other hand, if you have, you know, a deposition in a lake or in a shallow sea, or even dust coming down from the air that's getting cemented in place, it can take, you know, a lot longer. So we don't really have any idea yet as to the time.
And the depth of the water is also hard to gauge from.
We think that we've seen the water at the surface. We've seen the water below the surface, so we know that we have some, you know, fairly substantial thickness. But of course, so far we've only seen a few tens of meters. That's all we can really talk about for certain.
Yeah, I was wondering, what did you finally determine pot of gold was made of? It's such an unusual looking rock.
We did not do an analysis on pot of gold. That picture is the best picture we have of it. The problem with grinding something like that, the grinding wheel really needs a surface which is fairly flat, or else it can it can get jammed. If it's spinning around, it just hits it every once in a while. There's a lot of vibration, so we couldn't really put our grinding wheel on there. And at that point, I think we were trying to get up onto the side of the hill again to get our solar panels tilted in the right way. So we never did an analysis on that, and a lot of us have just been looking back at that. We've never seen anything like it since, and we sort of wish we'd been able to spend a little bit more time there.
I found a rock that actually looked like that when I was a kid.
Oh yeah, you can see these things. A lot of rocks, that especially that limestones and things that can get eaten out by slightly acidic water. It can form all kinds of weird shapes like that. Yeah.
If there is a water, there must be carbon and nitrogen compounds. Is there any evidence for this compound there?
Well, there's very little nitrogen to be found on Mars. The atmosphere has almost no nitrogen in it, and so nitrogen is one of the things that I don't think we've sent the proper instrumentation really get, because it's a trace element on Mars. There's plenty of carbon dioxide. I mean, the atmosphere is almost completely carbon dioxide. We've found almost no carbon in the rocks. So again, if the water was there and it was the pH was very low, it was very acidic, carbon doesn't like to precipitate under those conditions. And so we think, at least the places that we've seen, perhaps that's the reason why we don't see much carbon in the soil. Where the carbon's gone to is a good question. I mean, there's not, the atmosphere is very thin, and if you look at planetary abundances and accretion and things like that, there was a lot of carbon there at one time. We don't know where all that carbon's gone at this point, whether it's held in rocks that are deeper below the surface, whether there's loss mechanisms that are taken off the top of the atmosphere. That's still a mystery. And in fact, there's just a pair of missions that were selected for study just a few weeks ago that's supposed to look at the processes at the top of the atmosphere, the loss processes from the atmosphere, to try to understand how Mars might have lost the carbon and the water from its atmosphere.
There must be then microbes.
That's a possibility. We're looking at that too. Yeah.
Actually, really fascinated by the chemical analysis that was done. And I guess the comparative model is obviously, against periodic charts on Earth. Other things or elements that maybe could not have been identified, how do you go through that process of doing that comparative analysis of this is in fact carbon, or this is in fact whatever it is that you're analyzing, or are these things in fact all composed of things in the universe that we can find here on Earth? How do you do that?
Well, I mean, the way the periodic table is set up is that you add another proton, you add another neutron, you add another proton, you add another neutron, and you just start putting it together, and there's the elements are just determined by how many protons you have. So you go from 1 to 108, 112, whatever it is right now. Those are all the elements there are, and you can look at spectra of gas clouds from thousands, millions of light years away, and it's all the same spectra as you can see from the materials you have on the Earth. And so, as far as we know right now, there's no evidence that there's any other kind of elements anywhere. And certainly Mars, I mean, it's practically a next door neighbor. From a galactic standpoint, I mean, we're next door neighbors, and we wouldn't really expect it to be much different. It almost certainly formed from the same gas cloud that the Earth formed from. Slightly farther away from the sun, so the ratio of elements is a little bit different, but we don't really expect very much different. As far as the way those atoms get put together and the different crystals and things like that, certainly there may be different kinds of minerals. You can have different minerals that have exactly the same chemicals in them, but they're arranged different ways in the crystal structure, and you get things that look completely different, that act completely different. And so we certainly don't believe that we know what all the possible different minerals are. All we can do is look at the analysis results on Mars, try to compare them with things we have on the Earth, and when we get a good fit, both with the chemistry, with the mineralogy, and with the appearance, then we conclude that that is almost certainly the same thing as we see on the Earth. But you never know for sure until you pick it up and bring it back and put it in your mouth if you're a kid, I guess. Yeah.
Slightly off topic, but can you talk about the seismic instruments that you're proposing for NASA to send to Mars?
Oh, wow. Well, we've been working for a couple of decades now on developing very light, very sensitive seismometers, because a seismometer, it turns out, is the best instrument, bar none, for looking at the really deep parts of the planet, looking at the core, the mantle, and the composition of the deep planet. Because when seismic waves go through the planet, the frequencies, the wavelengths, and the properties of the waves are affected by the material they go through. And so on the Earth, we know that there's a core on the Earth because of seismology. We know the thickness of the crust because of seismology. We know the composition. All this stuff we've gotten from seismology. The Moon is the only other place in the solar system where we've done seismology. We put seismometers on there with Apollo, and it's told us about the upper 600 or 800 kilometers of the Moon. And so we know that the Moon has a very thick crust. We know that it has a mantle that's similar to the Earth's. The crust is a little bit different than the Earth, both from seismic analysis and from stuff we brought back to Earth. And so everything we know about the interior of the Moon, we know from seismology. Okay, so some of us want to know what's going on inside Mars, and so we're trying to send seismometers. But the problem is, one seismometer doesn't do you very much good because you have to be able to triangulate on the Mars quakes, and once you've triangulated, then you can figure out what the rays, the path that the rays took, and then you can start pulling out what the composition and what the depth distribution is. And so you have to send at least 3 or 4 or 5 or 6 of these things. And you start going ka-ching, 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 when you have all these landers. And so NASA's always been just a little bit hesitant to actually, sink that much money into it. But we've gotten to the point where, the conditions on the surface depend on the amount of water, the amount of gases that have been delivered to the atmosphere. That stuff all comes from the interior. It's related to the volcanic activity. And then we have the magnetic field, which today on Mars is dead, but we have crustal remnant fields which were set up in the crust a long time ago by very strong internal magnetic fields. We don't know where that magnetic field went. We don't know what the size of the core is, so we don't know what the dynamics are. They could have set up the dynamo. The magnetic field shields the atmosphere from the solar wind, and et cetera, et cetera. So it's getting to the point where we really need to know about the interior in order to be able to even talk about what the early environment was on Mars and how it got to where it was today. And so suffice it to say that it's a really, really good thing to do, but it's not very easy. But we're proposing some missions to try to get around some of the technical problems, and we've been working with colleagues in Europe who also have some of the same goals and trying to sort of pool our resources in order to be able to do a mission like that.
Good luck with that.
Thanks. Yeah.
Along the same lines as that, are any of the missions planned to purposely crash something into the surface to get seismic activity like they did with the Moon, with the third S4B stages?
That's certainly a possibility. I mean, we've done lots of studies. We studied one little mission that would actually send some little cannonballs about this big, and if you actually get them straight in there, you can actually put enough energy in that you can bounce seismic waves off the bottom of the crust. And if you have seismometers there, you can time that. Since you know the impact point and the impact time very precisely, you can just get the bounce time and get the thickness of the crust really, really, really well. Right now, like I said, we don't even have any seismometers on the Moon, so actually having something on there to make seismic waves is farther into the future. But you don't have to have something very big if it goes fast enough. Yeah.
What's your smallest functional seismometer down to now, size and weight?
We have a seismometer that's about an inch cube, okay? And that's as good as most sort of university class seismometers. It goes down to periods of about 50-second periods and then up to 100 hertz or so. We'd like to be able to get even lower frequencies because the lower frequencies penetrate deeper. And to do that, you actually have to have something about the size of, I don't know, there's no ball's the right size, but it's about this big. So at that point, you can get even the tides that are induced by the small moons of Mars that have periods of like 8 hours or so. So we have pretty small ones. One more question, I think we wrap it up. Yeah.
I noticed that a lot of the hills and rocks and craters had names. Just out of curiosity, who applies these names, and are they approved by the International Astronomical Union?
No, we just make them up. yeah, we make them up as we go along because if we're sitting in meetings. I mean, every single day, we have a meeting in the morning for each meeting for spirit, meeting for opportunity. We look at the images that came down. We decide where we're going to go next, and you can't say the feature at latitude 28.358 longitude. So we say we're just going to call this Raquelme. We're going to call this Victoria. And Victoria actually is a name. And so these are all just informal names, and we're supposed to put quotation marks around them whenever we use them in official presentations. Some of the names we've applied to the IAU, the International Astronomical Union, to get official status. Most of them, they don't care about rocks. They don't care about ditches that we've dug with the wheels and things like that. But like the hills. Some of the craters, some of the features on the hills, we've applied for names, and it takes about anywhere from 2 to 100 years to get the IAU to weigh in on it. So, but most of these names are just informal names that whoever happens to get up at 8 o'clock in the morning to go to the meetings can make it up. So, okay, I'll take one more.
Your best guess as to the early history of Vosloh crater? Was there a huge volcanic period that filled in that crater? Or?
We think so. We still think it must have been a lake. I mean, you look at the morphology from orbit, and it's just really clear that a lot of water flowed in there, and even went over the top and went out the other side. And so there must have been some fluvial activity, water activity in there. Since that time, we think that there's been a lot of flows that have covered at least the area around our landing site. And then subsequent to that, it's been beat up by meteorites. And so we think if you could get down far enough, you probably would find basalt layers. And then below that, you'd probably find some sedimentary stuff. All the basalts that are in there came from somewhere, and they couldn't come from very far away. We think that small meteorites hit and pulled these rocks up, buried the layers, and that's what we see now. So we haven't been able to identify the vents or anything like that, but most of the lava flows on Mars don't have identifiable vents. So we think that was the sequence. We have no idea what the actual time was, whether it happened 1 billion years ago, 3 billion years ago. No way to tell.
Are the hills suggestive of geothermal activity, like Yellowstone type environment, or?
It's possible that there was geothermal activity. We think there was some geothermal activity. We don't know whether it was it got to the surface like at Yellowstone, or whether it was similar to that. But most of these rocks formed under reasonably high temperature. Were altered under reasonably high temperatures in the presence of water, at least for a little while. Again, perhaps if these hills were formed by volcanic processes, as that heat was cooling down, it could have set up temporary hydrothermal systems. Again, that's kind of speculative. Okay, well, thanks for coming.